Hello and welcome to this Let's Talk Meshing video. In this video we're going to address advanced structured gridding techniques with specific emphasis on maximizing your productivity in generating these multi-block structured grids while balancing cell quality and solution accuracy. Before we begin, let's go over a quick overview of what we're going to talk about in this video. First of all, we're going to start with some motivation. Why do we want hexahedral? What benefits do those offer for our CFD solvers? Then once we've established why we want to pursue this and why we should expend the effort to generate these structured grids, how do we generate structured grids in non-ideal shapes, such as triangles, circles, spheres, etc.? Then we're going to touch briefly on how to work with extrusions in pointwise and some of the settings that you can use to get better results out of those. We'll then talk a lot about volume topology creation. So this is one of the large time sinks whenever generating multi-block structured grids. And we're going to talk in particular about some utility scripts and showcase how scripting can really expedite the process and help you increase your productivity when generating these multi-block structured meshes. And then lastly, we'll touch briefly on hexahedral T-Rex meshing techniques. T-Rexes are unstructured viscous meshing algorithm that produces boundary layer cells there near your surfaces. And in 17.2, we've actually introduced the ability to recombine these into hexahedral cells. So you're able to get the benefits of hexahedral cells in your boundary layer while not having to deal with the complex volume topology required for multi-block structured grids. So first, let's discuss hexes and what advantages they have. For cell-centered codes, which I'm going to focus on today, cell-centered codes have an implicitly larger computational molecule with hexahedral cells. That is, a hexahedral cell, it's in the name, it has 6 faces, whereas a tetrahedral cell only has 4. More faces means it has more neighbors. That means it has more information about local gradients. And you can also have special properties not present in tetrahedral cells. For instance, face pairs. For an orthogonal hexahedral grid, face pairs can be aligned perfectly with the flow, and just by having pairs of faces as opposed to 4 somewhat randomly oriented faces, as you get with tetrahedral cells, you're going to have less likelihood for numerical diffusion. The flow alignment can be a big thing. If you have perfectly flow aligned cells, you actually reduce some of the computational errors introduced when computing fluxes across multiple faces. And then this last one isn't necessarily an advantage, but it is a feature of hex grids, and that is that it approaches a 1-to-1 cell-to-node ratio. That's very useful if you're trying to use the same grid in a cell-centered code and a node-centered code, and you want to have roughly the same number of unknowns going to the solver with the same resolution. Tetrahedral grids actually get close to a 6-to-1 cell-to-node ratio, so you can wind up with vastly higher cell counts for a given resolution as dictated by your node count. Now, a quick little illustration here of what I'm talking about. On the left, you see a tetrahedral cell. This is just kind of an equilateral pyramid, you might say. And then you have with a triangular base. That's an important part. So every face is a triangle, and it has 4 neighbors associated with it. A hexahedral cell on the right has 6 neighbors, and in this perfectly orthogonal case, you can see that if the flow were perfectly aligned in this direction, all of the flux being computed whenever you compute the quantities being advected from one cell to another are going to be perfectly confined to this single face pair. Another thing that I should point out is while both of these shapes are inherently 3-dimensional, the neighbors surrounding a hexahedral cell must lie in 3 dimensions if it's a properly formed hex cell. However, for a tetrahedral cell, there are configurations where each of the 4 neighbors can actually lie all within the same plane. And so even though it's a 3-dimensional cell, you're really limited in the amount of information you have on gradients in that 3rd dimension, should those points lie in a certain configuration. Problems that we can run into on the solver side include non-orthogonality and skewness. There's other issues as well, but we're going to focus on these 2. Non-orthogonality you hear a lot about, and that tends to creep into the solution or the error in the solution whenever you have misalignment between a face normal vector and the vector connecting adjacent cell centers. So whenever you're going and discretizing your equation, in particular you're discretizing the Laplacian term in your equation, you wind up with a dot product of the face area vector, SF, with the gradient of whatever field you're computing, grad phi. whenever you discretize and use this approximation, the gradient is approximated as the difference, in the most simplistic case, as the difference between these two cell centers, and therefore inherently the gradient is along the direction between those two cell centers. That's not necessarily where the actual gradient lies, but whenever you are using this approximation that is CFD, it's just one of the results. Since we have to compute this dot product, you can actually introduce some error because you are doing additional manipulations to these already approximated quantities, and so you can introduce error to this diffusive term. Now, skewness, on the other hand, arises primarily from an interpolation error. And again, I'm only talking about the lowest order methods here, where you're computing the face value advected across this flux by using the interpolation between these adjacent cell centers. In the presence of a vertical gradient here and a horizontal velocity field, if the value that is going to be advected across this face is going to be misrepresented whenever you use the cell-centered values, because the value at the face is going to be inherently different than the value here as computed through the interpolation of those cell centers. There are some higher order terms that you can include to increase the accuracy, but in general, these trends are going to remain the same no matter which algorithms you're using, which methods you're using to compute these. The idea is if you can eliminate the sources of the error, the non-orthogonality or the skewness, you're going to wind up with a higher quality solution regardless of your specific solver settings. Now, whenever we went about starting to look at the effect of the grid on the solution, I wanted to pay particular attention to numerical diffusive terms. Now, since any sort of numerical artifact is going to add to a diffusive term here with non-orthogonality, the thought was, as a first pass, let's examine the skewness, because here you can actually use a simple test case where you have no diffusion by considering only pure advection, and any sort of diffusion that we see at all is going to be a result of numerical errors creeping into the solution. We're not trying to look at a diffusive error on top of a diffusive process, if that makes sense. So the test case that we came up with was the advection of a passive scalar. You can think of this as a temperature field being advected across a non-conductive fluid. So what we have is a simulation domain. We're imposing this hyperbolic tangent profile at the inlet, and then that profile is just going to be advected across the simulation domain from left to right. Because there is no diffusion in the solution, in the solver, any sort of deviation from this profile is going to be due entirely to numerical artifacts. Further, because we're just advecting the flow across, we know precisely what the value is anticipated to be, what it should be at every point in the mesh. So whenever we take a step back and look at just a baseline case, this is a perfectly orthogonal structured grid in 2 dimensions. Whenever you look at the error here, you see we have very negligible error, fractions of a percent, and that residual error is simply due to the linear interpolation of this nonlinear function. Because we at some point have to cut off the resolution of our grids, I think this case was 200 grid points by 200 grid points, you're just going to wind up with some finite interpolation error from your discretization of the solution, of the imposed boundary condition. So this baseline error is just the bottom line that's as good as the solution is going to get with this linear solution. Now, whenever we start adjusting our grid, now if we take that same orthogonal grid and we rotate it 20 degrees with respect to the flow, you now see that we actually are introducing some appreciable error into the solution. This is because we've now introduced a somewhat preferential direction, and whenever you're computing the flux, it's no longer going through a single face pair. It now has to divide itself between 2 faces. And in doing so, it's going to introduce something that's sometimes called a numerical mixing process. And what that does is it preferentially migrates this gradient upward slightly, resulting in a lower velocity or lower temperature profile than is theoretically expected at these points. Now, again, the error here is small. I'm not saying that you cannot sustain and cannot handle non-flow aligned cells. I'm just simply pointing out that these cells will introduce some error into your solution, and it's up to you to kind of mitigate those and decide whether or not that's going to be a large enough effect on your solution. Now, more impressively, perhaps, is if we go to a triangular mesh, and in particular we're going to look at a Delaunay triangulation. Here we now have a significant amount of numerical diffusion entering our solution, a significant amount of error accumulating, because each of these cells, just a nature of the Delaunay algorithm, is going to produce a cell with some non-zero skew. In fact, the distribution of skewness in these Delaunay meshes is roughly a normal distribution. So there are a lot of cells that have very low skew, but then there is a tail of cells, a probabilistic tail, that has significant, if not even high, skewness in these triangular cells. What that does is it introduces a cumulative error. So as the profile is advected further and further downstream, these errors compound one another, and the overall error in the solution grows larger and larger. Here on the right, this is a heat map showing the skewness of this Delaunay mesh. This is actually a much coarser mesh than the simulation was run on, but this just showcases how you have this random collection and random assortment of skewness. The more red the color, the higher the skewness of the individual cell. These effects can also be extended into 3 dimensions. In this case, I actually used a cube with 100 cells on each side, amounting to a total cell count of 1 million hex cells. And whenever we use a perfectly orthogonal grid and we impose a Gaussian temperature profile now, so we have some 3D effects as opposed to a simple vertical gradient we had in 2D, you can see that the hex grid does a very good job of maintaining the errors. The residual errors that you see here are, again, just due to interpolation errors, the limits in the resolution of our grid. But the important thing is that the solution error does not grow over time. So these are slices at 3 positions downstream. So this is near the inlet, around halfway through, and then near the outlet. This is a cross-section showing the full plane. You can very faintly make out the small interpolation error there. And this is a cross-section down the middle of the plane that shows, again, the profile having negligible error throughout. Now, whenever we look at a tetrahedral grid, the picture changes dramatically. So despite having the same edge count on the outer boundaries of our cube, the tetrahedral cells, because of that 6:1 node ratio, actually produces a grid that has over 6 million cells. So this is a fairly large grid for such a simple test case. However, because of this non-zero skewness throughout the volume, we wind up introducing error that accumulates more and more and more as the solution is propagated throughout the volume. So you can see now we have appreciable error. The error starts off relatively small, it grows larger, and it grows larger still. The point of this is not to cast doubt on unstructured grids and unstructured solvers in general. In fact, many commercial codes contain more sophisticated algorithms that help mitigate these numerical errors on unstructured grids. Rather, the point is simply to highlight the tendency for tetrahedral grids towards numerical diffusion and to showcase a specific tailor-made example where the unstructured grid does not do an adequate job of resolving this sharp gradient. This is just kind of a best practice sort of approach. The idea here is not that a tetrahedral grid will always introduce this much error, but rather, if you can avoid using tetrahedral grids in regions with very sharp gradients, such as a boundary layer, you're going to be able to achieve a more accurate CFD result, regardless of the algorithm that you're using. In fact, this is one of the primary motivations for the T-Rex feature in Pointwise, which allows you to create these high-quality prismatic boundary layers, or now with this new feature, hexahedral boundary layer elements, to help really resolve your boundary layer and those regions of sharp gradients while maintaining the flexibility of this unstructured tetrahedral far field. So now that we've kind of motivated why you want to use hex cells, hopefully you can see that hexes certainly have their clear advantages in certain circumstances. Let's talk about how you go about generating these topologies. Unfortunately, most of the time for realistic geometries, we're not faced with very simple, straightforward grids such as this one, where we can generate a structured grid very easily. So in the following slides, I'm just going to talk a little bit about how you can go about creating good quality grids in an efficient manner. And to begin, let's just set some ground rules. What I mean here by a quality structured grid is a max equiangle skewness of less than 0.6, a maximum included angle of less than 140 degrees, and entirely composed of quadrilateral cells. I'm just going to be working in 2D right now, but these are easily extensible to 3D, and we'll do an example later on that'll kind of showcase that. So one of the first steps is, okay, what if you have a nice orthogonal domain, but our edges simply don't match up? In order to create a structured grid, we need to have opposing edges match in their dimension. And so you can see here the upper dimension is 10, the lower dimension is 11, and that's not going to be able to create a good quality structured grid. In fact, you can perhaps put a triangular cell in here with a pole and generate a quasi-structured grid, but that breaks our rule of being comprised of entirely of quadrilateral cells. So whenever you encounter a case like this, go back and look at the topology downstream, or upstream, I should say. Why is this dimension 10? Is it possible that we could redimension this and get a balanced domain so that we can generate that nice orthogonal structured grid? More often than not, we're actually faced not with dimensional imbalances, but actually geometric constraints. So take, for instance, this circle. So we have a nice uniform spacing around the edge. We could theoretically generate a structured grid in this domain because the opposing edges are balanced, but the geometry has imposed a very hard constraint here in that this maximum included angle is going to be very, very large and is dictated by the boundary. And that's simply because we're putting one corner of a cell here and then splaying that cell outward so that the adjacent edges match up. So no matter how much you refine this grid and how many points you put in this, it's always going to contain a few highly skewed cells. You can run the elliptic solver on this also and kind of mitigate some of these errors, but no matter what, because you've placed this constraint here at this junction, you're going to always have at least 4 poor quality cells. So this is not really a good topology for geometries like this, but instead we can introduce internal topology and obtain a very good quality grid. So by introducing this internal topology that's sometimes called an OH topology because the grid lines on the outside form this O pattern, on the inside form this H pattern. It's not the naming convention I came up with, it's just the one that stuck, so we'll live with it. So these grids can produce very good quality cells throughout. You have excellent orthogonality near the edges, which is great for boundary layer resolved flows. If you wanted to, you could go back in here and very easily apply a viscous spacing here. And so this topology is very, very good for these circular or rounded geometries. Similarly, you might be faced with a domain that looks like this, where you have kind of this half circular geometry. And you might think, okay, well, if we can put a good structured grid on a full circle, we could certainly do one on a half circle, and indeed you can. Again, it follows the same pattern. You can introduce internal topology here, and you essentially wind up with a result that closely resembles that OH topology we saw before. Now, and if we look at the skewness, you can see again that we have very good quality cells throughout. Another case that you might encounter is some combination of this. So here, again, we have a balanced set of connectors. We could theoretically put a domain in here as it stands, but whenever you do so, you're going to wind up with large swaths of your grid that have very high skew. And that's not advisable or desirable at all, for that matter. So again, by introducing internal topology, we can draw a connector across here. We can then create that semicircular domain up here in the top, and then a regular H grid down below. And this results in a very low skew, high quality grid. Now, another geometry that you might encounter whenever you're doing realistic geometries is a triangular region. And if you sit back and think about this for just a little bit, it's not immediately apparent how you're going to fill a triangular region with quadrilateral cells. But as it turns out, there is in fact a unique solution, at most one unique solution, that allows you to put a fully structured grid in this sort of geometry. Unfortunately, doing this by hand is a little tedious, actually. It takes a little bit of trial and error, and you can kind of guess, but you have to adjust some dimensions and all that. But as it turns out, there's 2 constraints, and so long as the edges of the triangle satisfy both those constraints, the grid is possible to be made. The first constraint is that no one edge can be longer than the sum of the other 2. That just goes back to basically the triangle inequality from geometry. And then the second constraint is a little odd, if you'll pardon the pun. The sum of all edges, the sum of the dimension of all edges must be odd. So in this case, we have 13, 17, and 15, the sum of which is 45. That allows us to create a nice, good quality structured grid in that area. However, if we reduce one of the dimensions to 14, the sum is now 44, and this is actually impossible. So this is the sort of thing that is very lends itself very well to scripting, and so there's a script that's been developed as well that we'll demonstrate here in just a minute. Now going to a realistic geometry now, this is actually a cross-section of the scroll of a volute. We're actually going to come back and create a volume topology for this at the very end, but for right now let's just go through how you might think up the topology for a shape such as this. The first thing when I look at this that jumps out at me is this inlet shelf here. So this is a roughly rectangular region, so if we just introduce a connector across here, we can put a regular H domain in here without much issue at all. So that's kind of the first step, is to kind of get the easy parts and whittle away at it. The next step we have here is we see that this is a mostly circular region. We'd really like to put one of those OH topologies in here, but because of the way it connects right here, we're not going to be able to do that right away. What we can do though is we can inflate these layers off of the edge until they meet up here at the center point. That's going to give us some boundary layer blocks here around the outside, and then leave us with 4 connectors here on the inside that we can then create an OH topology with. So we can create this grid on the outside, we can get good orthogonality here, we can then introduce the OH topology on the interior, add the grid to that, and then we have a very good quality grid on this fairly complex and realistic shape. So at this point I'm going to hop over into Pointwise actually and pull up some examples to kind of demonstrate some of the things that we can do. So the first thing is we're going to demonstrate this OH topology. So as I mentioned before, this can be done with a script, and we have a script on our GitHub repository called CreateOH that will do just that. In order to run this, you simply highlight the connectors, you go up to Script and click Execute and navigate to the script. I've already queued them up, so I'm just going to pull the script up right here. It's going to bring up a GUI that asks you for some input, and what I'm going to specify here is a radial dimension of 7. Whenever I specify a dimension of 7, that's simply telling it how many grid points to put along these radial connectors. You then click Create OH, and then it automatically generates that topology for you. So you can see that's a very rapid process. There's no, minimal human intervention there. You simply select your connectors, and then run the script, and it'll generate the topology. Similarly, this sort of approach can also be extended to these half circle domains as well that consist only of 2 connectors. So in much the same way, we're actually just going to highlight those connectors, we'll go up to script and run the semicircle script. The semicircle script doesn't actually require an input because the dimension of this flat piece here actually dictates what your radial dimension can be. So whenever you run this script, it automatically determines that, generates the topology for you, and voila, you have your topology within a matter of seconds. This doesn't have to be a perfect circle either. If you have 2 connectors that form some area such as this, you can run the script on the same script on this topology, and it will automatically generate the topology for this as well. And so you can see that the script produces these very good quality cells throughout. You have good orthogonality everywhere and really negligible skew throughout as well. The next thing is this triquad. So this is a script that will generate those quadrilateral domains in this triangular region, and it runs in just the same way. You simply highlight the connectors, you go up to script, navigate to the script in your directory, or as I have it here, just queue it up. We highlight the connectors, run the script, and it generates the 3 quad domains here. Now, as I mentioned before, this is very sensitive to the dimension. So if you look down here, whenever I hover my mouse over this connector now has a dimension of 14. So it's not dimensionally consistent with that criteria I put forward earlier. So if you try to run that same script on this set of connectors, you'll see down here in the message window that the sum of all connector dimensions must be odd. So it's not going to be able to generate that topology for you. Now, if we look at another commonly encountered geometry or feature that you might run into, are these fillets. So in this case, we have kind of this rectangular duct with some sort of rounded corners. There's 2 ways that we can do this. One, you might look at this fillet and say, you know what, this is really just a quarter of a circle. So what if I was able to create a quadrant of this OH topology like this here in these corners, and then connect up the other parts with just simple H blocks? The other approach is you could actually just create an OH topology in the entire thing. And so we'll kind of compare these two. So the first thing we're going to do is we're going to create these little corner blocks that I call them. So you simply highlight these connectors here. You then go to script and run this script that I've named fillet. So whenever we run this script, it's going to go in and create these quadrants for us based on this local curvature. And then what we can do is we can actually run another script that I'll talk more about later that will take these other connectors and fill in. So we simply highlight the connector, run the script. I'm just re-executing with Control E here. And then create this internal topology pretty quickly. We can then highlight all of these connectors, assemble the domains. We'll need to create that inner part as well, highlight those connectors, create domains. And you can see we now have a very good highly orthogonal domain here in the center. Now, if we were to just use the create OH script to generate an OH topology here, that will work. It will create a decent grid in that space. So we're just going to go back up and look in the recently executed and click create OH. We'll just use the default number of dimensions, create OH. And so you can see that this gets a good orthogonality in the edges. It gets good orthogonality in the core. But if we look closely and we grab all those domains and we go up here to the examine, look at angle skewness, you can see that by doing the corner blocks, we've restricted the cells with non-zero skew to a very small region here near the corners. Whereas the OH topology just inherently generates a large number of cells with appreciable skew further into the volume. So it really kind of depends on your particular circumstance, what you're trying to get after. If you can afford this additional topology here, you can wind up with a higher quality grid overall and kind of confine the problem areas to a very small local point. Or you can use kind of a larger global script that will produce fine results. It's just, again, it's a matter of kind of balancing your cell quality and your solution accuracy. One interesting thing about this fillet script, though, is it is actually useful in 3 dimensions as well. So here we have a block that's, or a shape that's representative of some sort of fillet in a geometry. This could be between the blade and the hub. It could be between the root of an airfoil and the body. But these types of geometries are sometimes problematic to create structured grids on because you don't really know where to feed this topology. It can be somewhat problematic. So the fillet script is actually very useful for rapidly generating blocks here in these regions. So if we just highlight these 2 end connectors there and we run that fillet script again, what it's going to do is it's going to create these domains that can kind of form the end caps for a block here there on the fillet. And so because of the formulation here, it's going to ensure that these points are orthogonal to the surface. We can then use that FJsqCI8y8Y script that I used earlier to generate the rest of this topology. So the squeeze connector script is really just a combination of 2 operations. I'm going to go ahead and highlight that connector and execute the script. The first operation is a translation. So you highlight the connector and pick 2 points. It's translated to the closest of those points. And then it scales that connector to fit between, to make sure that the other end matches up with the second point that you've chosen. Whenever you have connectors that are closely resemble the final shape that you're after, this can be a very robust and quick way to generate this volume topology. However, if you have a lot of twist or a lot of 3-dimensional motion or movement or 3-dimensionality to the connector that you're trying to scale, it's not going to behave very well. You kind of need to split that up into smaller chunks and handle each one individually. For instance, if you tried to take a line and scale it into an arc, there's really no way of doing that robustly. Once we've generated that topology, though, we can highlight both the domains and the connectors here, and then just click on Assemble Blocks. What that'll do is that'll generate 2 blocks. We have now a block right there next to the fillet, and then we have this corner block here. If we wanted to, we could actually grab this connector and using grid dimension or the Control W hotkey, we could add points to it so we can get some viscous resolution. We can then go through, and highlight these 6 spacing constraints here so that we get a nice tight spacing there near the wall. And I'll just type in 1e to the minus 2 there for that spacing. And so you can see that we now have a nice, very good quality boundary layer resolved block. And moreover, we've now presented 2 orthogonal faces that can be used to construct the blocks coming off of the blade and the hub. So the point of this is I hope to kind of stress how you can use these scripts to really expedite this structured gridding process, and can really kind of take some of the onerous tasks out of creating these multi-block structured grids and make it a lot more, streamlined, is kind of the word I'm thinking of. Let's hop back over to the slides for a minute, and let's talk about some of the other tools in Pointwise. The first thing I'll talk about is the elliptic solver. Pointwise has a lot of settings in the elliptic solver that can really help you achieve a better quality grid whenever the initial grid just isn't quite up to par. Now, a couple of guidelines though for using the solver. You always want to check the underlying entities first before you go about using the solver. The solver should sort of be thought of as a last resort. Most of the time, if you have a strange area in a domain, what's probably going on is there's some error or some poor distribution of points along one of the connectors. And likewise, if you have poor quality cells in a block, a lot of the times that can be due just to a poor quality domain. So always check those first before you go into the solver and start fiddling with things. Also, something to be aware of is that different algorithms can provide different behavior. For instance, the von Levante-Hilgenstock White algorithm tends to maintain clustering, whereas the Steger-Sorensen is a little more relaxed in that manner. So you kind of need to develop some familiarity with those. Try both and see which one gives you the result you're looking for. A very important point is running the solver is not required on all domains or blocks. In fact, in most cases, if you've been diligent about creating your surface grid or your connectors to generate a domain, you're not going to necessarily even need to run the solver at all. You should think of the solver, as I said, as a last resort to fix problem areas when you have some sort of strange shape that needs to smooth some grid lines or something like that. But by all means, don't think that you need to run every domain. And along those lines, running the solver for more iterations is not going to give you a higher quality grid. In fact, in some cases, that can wreck a grid that's perfectly good from the onset. Also, if you have just one small area of a grid that needs a little more work, you can use subgrids to isolate those problem areas. That way you're not unnecessarily running the solver on other portions of your grid that are already of sufficient quality. Another good point is that you do not want to assume that the defaults are always going to be correct. The defaults are there just because we needed something to go to, but that's not to say that they're what you should use everywhere. Something that I want to talk about in particular are the spacing and angle controls. By default, the spacing control is set to interpolate, and the angle control is set to orthogonal. In a lot of cases, this works very, very well, but in some cases that I'll demonstrate a little bit later, your angle control in particular can really produce very poor quality results if you don't change that from its default value. I'll also go quickly over the boundary conditions. The boundary conditions refer to these outer edges of your domain and how the grid points are treated on those edges. A fixed boundary condition means the grid points on those edges stay fixed and don't move. Floating allows both the grid points and the line containing those grid points to float around if the surrounding domains are all loaded into the solver. And then finally, the orthogonal boundary condition allows points to slide along an existing curve, but the curve itself is fixed in space. So that can help you get kind of redistribute the points more optimally. So another thing that we'll talk a little bit about are the extrusion tools in Pointwise. Pointwise has some hyperbolic extrusion tools that can be very, very useful for rapidly generating at that, boundary layer resolved structured grids. However, they can be a little bit finicky. Particularly, hyperbolic extrusions tend to fail a good bit of the time whenever you have severely concave regions like this. This is because as this front marches outward, the grid lines try to cross over one another and the extrusion fails because it's produced a cell with negative volume, for instance. Whenever you have or presented with cases like this is, for instance, the slat cove region of an airfoil, what you can do is you can first turn up Kinsey-Barth to a value greater than 1, maybe a value of 2 or so. You can also turn down volume smoothing for the first few layers, and you can also start with a much lower step cell height if you can accommodate a lower Y+. The other thing to keep in mind is that extrusions are going to behave best whenever they have a nice uniform surface grid to start from. So if you have a rapid jump in cell area, for instance, or cell spacing, node spacing on a connector, the hyperbolic extrusion is going to potentially fail for that. So those are some things to kind of try. Extrusions can be a little finicky, as I said, but by kind of playing around with some of these parameters, you can, of course, change these parameters as you extrude outward as well. So you can turn down volume smoothing for the first few layers to get out of these problem areas, and then turn it up so that you get nice uniform cells further out. Another extrusion tool I'll talk about are the path extrusions, and here you can generate a single topology at the outlet and then extrude that along a connector to rapidly generate three-dimensional blocks from that. So here, these are just a couple of tubes from, say, a heat exchanger or something like that. The only downside to this is that the path extrusion requires a constant cross-section. So if your cross-section changes along the path you're extruding along, then the path extrusion isn't going to work, unfortunately, and you'll need to generate that topology by hand. So speaking of generating the topology by hand, some techniques for blocking in 3 dimensions. The first thing I always do is I consider the connectivity of ideal blocks. So this is an aneurysm that we did a video on a while back. And I looked at this, and you have 3 arteries that enter this junction, and each of those is a circular pattern. So you can say, all right, well, we're going to have OH topologies here, and then how can I connect that up to be a consistent topology for the full geometry? So you can then kind of get out a sheet of paper, try to do some 2-dimensional sketches, and say, okay, well, we're also going to need an OH topology here, but then it's going to need to combine down here at some sort of end cap, since we can't have an edge on this outer feature here because it would produce highly skewed cells. And then you can also just kind of mentally split these geometries up. This is a volute that was provided by Aerodynamic Solutions. And whenever I see this geometry, I kind of think about it, okay, well, this inner piece here, this inlet shelf, could be split off as an annular region. That would be very simple and straightforward to mesh. You can then also say, okay, well, these segments of the scroll could also be meshed individually and would be fairly straightforward. It's just a circular cross-section, albeit one that's changing as a function of the angle around the volute. But generically speaking, that's a fairly straightforward topology, and we'll actually mesh this in just a minute. So that really reduces this entire geometry to one area here near the tongue. And so what that allows us to do is quickly come up with a topology throughout the majority of the volume and then focus our efforts on the difficult areas. Whenever we do that, we go back and we consider these remaining voids, and we try to maximize the cell quality in this. For instance, one potential topology here was actually taking these grid lines as they came around the volute and feeding them through and depositing them on the far side of the volute wall. The problem is, whenever you do a topology like this, you can think about it and you can say, all right, well, that's possibly going to work. But for instance, in this case, because the cross-sectional area of the scroll at this point and near the outlet here is such a disparate scale, we're really going to need a different topology. That's not going to work, and additionally, that's not going to allow us to resolve these feature lines in the model that we really want to keep. And then also you can weigh in dimensional constraints, etc. And that may rule out a couple of your topologies. But then you can entertain another idea, and again, 2-dimensional sketches work. And for this case, we found that, okay, well, we can actually feed part of this grid around and feed it back onto itself, whereas the other half just kind of forms this closed loop there around the inner inlet shelf region. And then you can look for ways to keep the grid flow aligned, and you can eventually develop this consistent topology. I'm not going to say that it's going to be straightforward for every case, but it's something that you can think about and kind of work through. So constructing the volume topology is one of the most tedious aspects. And so I'm going to step through this example real quickly to show you how you can generate structured grids in a fairly quick manner by using some of the scripts and some of the techniques that we've talked about today. So let me pull up this model here. So I have the volute model, and rather than do the whole thing, I'm actually just going to do one segment today, just for the sake of time. The other segments are very similar. The tongue region requires a bit more user interaction, so I'm going to relegate that to exercise you can do on your own. But what we're going to do is we're going to just highlight this segment, and I'm just going to create a grid on it using the domains on database entities, and then I'm going to hide the database since we don't need it for the rest of this. What I used here was just a constant dimension here, so we actually need to redimension this to get better resolution. So I'm going to take those long connectors and change their dimension to 81. I'm going to use the Control W hotkey to dimension the azimuthal direction here at 41. And then what we have now is a pretty good surface mesh. As I said before, this is that cross-section that we looked at earlier, that whistle shape. What we might want to do next is actually create this inner inlet block. So what I'm going to do is I'm just going to grab this 2-point connector. I'm going to connect between these points, and then I'm going to repeat on the other end. So grab that point, grab that point. We can then highlight all the domains and connectors and click on Assemble Blocks, and that's actually going to create our H block there on the inlet shelf. So you can see in a couple of clicks we've already got the inlet shelf meshed. Now, if you were very particular, you might want to go back in and adjust this connector here so you get slightly better orthogonality here near the wall, but I'm going to skip that step today just for the sake of time. So the next thing I'm going to do is I'm actually going to go ahead and split this connector, because remember what we wanted to do is we wanted to inflate these boundary layer blocks. So I'm going to go ahead and split that at 50% because we want to make sure that we get equal number of grid points on either side here. The other thing I'm going to do, well, I'll repeat it on the other end for one, so Control Q to bring that back up, split it at 50, and click OK. The other thing I'm going to do is I'm going to go ahead and split the outer part into our 4 pieces for that OH topology. Since I gave it a dimension of 41, I know that if I split it at 11, 21, and 31, we're going to wind up with a nice evenly distributed set of connectors here. So there's 31. And that's going to leave us with 4 connectors here that each have a dimension of 11. So the next thing that we want to do is we want to create that boundary layer block. What we can do is, again, use a script to kind of help create that. You can try extruding this, but because it's kind of an odd shape and all this, it's a little easier for me to actually just generate by hand. So what we're going to do is we're going to highlight this and run this other script that I've written called scaled offset. This has a hard-coded parameter that you can change that's currently set to 0.75, and it just scales the loop of connectors that you've passed to it by that parameter, by 0.75, with respect to the centroid. So it's just going to scale that and create these new connectors here right there in the middle. We can then go in and edit these curves, so edit curve, and I'm going to change that over to catmull rom, and then add a point here up at that split point that we just added a moment ago. Then going to kind of delete some of these control points so that it's a bit, well, so it more closely matches the outer wall there. And then we're going to repeat over here. So Alt-EC is kind of the quick way to get there. Then we're just going to add a grid point there. Click OK. We're going to repeat this process on the other end. So highlight those, script, scaled offset. We're then going to just delete these 2 points, and then Alt-EC, change the curve type, go up here. We're going to actually just delete that point and delete a couple of these, and then maybe move this point around. And again, this is just to kind of make a nice smooth curve. This isn't going to be an optimal grid. I'm making it fairly quickly, but with a few more minutes, you can actually get a much, you can improve the cell quality a good bit. The next thing that we're going to do is actually generate those boundary layer domains. So I'm going to go up here to create a symbol special and then domain. I'm then going to just click the outer boundaries here, and then click next edge. Select the next edge. Control F is the hotkey to select that, and then click over here. I'm going to repeat the process on the other side. So rapidly generate this. Control F, click the next edge. Control F, click the next edge. So now we have our boundary layer domains. I haven't added viscous spacing. It's fairly straightforward to do that. But what I'm going to do next is actually split this up into those 4 pieces, just so that we can kind of more clearly see this OH topology that we're going to be putting in just a minute. So the next thing, I'm going to split these as well. Split, 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 and there we go. Something that I'll point out at this point is if you go in and look at this, you can see we actually have really bad orthogonality here. This really doesn't look very good at all. So what we're going to do is we're going to use that elliptic solver I talked about earlier to kind of improve the cell quality here. So I'm going to go ahead and highlight these 4 domains that are nearest the inlet shelf. The others actually look pretty good. And then I'm going to go up to Grid and Solve. I'm going to go to Edge Attributes, first of all. I'm going to highlight these edges that are on the surface of the volute, and I'm going to change that boundary condition to orthogonal to allow the points to move around. I'm then going to highlight these inner points here, and because these edges here start at a fairly significant angle and stay at a fairly significant angle, I don't want to use the default orthogonal angle control, because that's going to try to get this grid line to come off orthogonally to that surface, that edge, and that's really going to produce a poor quality result. So instead, I'm going to change that from orthogonal to interpolate. Then going to go over to Solve and run it for 5 iterations. And you can see that even after 5 iterations, we now have much better orthogonality here, and we have a much higher quality grid overall. The next thing that we need to do is create that OH topology, so I'm just going to highlight these 4 connectors. We're going to go Script, Create OH, and then click Create OH. I'm going to repeat down here. We're just going to use that default value. Control E will re-execute the script, create OH. So you now see that we have our outer topology. Unfortunately, we can't just highlight these and generate our blocks directly because Pointwise doesn't know about that inner H block. So we need to create the topology there as well. But we can use that squeeze connector script that we used earlier to translate and scale these connectors on the outside edge to fit between these points. So I'm using this bottom connector here, and then I'm just clicking between points on that inner H block, the corners of that inner H block, and then we've created that inner topology. We can highlight these connectors now, and then I'm going to actually highlight both the connectors and the domain here for that inner H block, and then click on Assemble Blocks, and you can see that we've created one block. The next thing that I need to do is I actually need to split this so that we have a connector here to create that radial domain. So I'm going to go ahead and use Control Q there, and then click on that point, change the direction so that it's in the direction we want. And then I'm going to, again, highlight the long connectors, and then I'm going to highlight these radial connectors here. We're going to do it on both sides, and then same thing down here. And bear with me, one more connector, there we go. So now we have those. We're just going to click on Assemble Domains. That's going to create 4 domains, these radial domains there. We can then highlight all the domains, click on Assemble Blocks, and if we now grab the blocks, you can actually see, if we go up here and examine the equiangle skewness, we've created this grid that has a max skewness of 0.72 or so. We could do a lot better. That max skewness is coming in here, and we could definitely improve on that by moving that around a little bit. But if we go over here and examine some cuts, you can see that we have a very good quality grid overall, and it really didn't take us that long to generate. So I hope that kind of expresses, kind of conveys how you can generate some of these structured grids very quickly and efficiently. Now going back over to the slides, just to kind of wrap up, the last thing I'll talk about are using structured grids for T-Rex. T-Rex now allows you to create these hex layers in an unstructured block, and that really is kind of the best of both worlds because you don't need to worry about the internal topology, but you're able to obtain hexahedral cells in your boundary layers, which are critical for resolving those gradients for reasons that we discussed earlier. So you can use those scripts that I talked about earlier to create these grids in, say, triangular regions or semicircular regions, and you can create these nice isotropic grids. T-Rex loves to have a very uniform surface grid, so whenever you're doing this, try to make sure that you have a nice uniform surface grid, preferably with an aspect ratio of the surface elements around 1 and small max angle. It likes orthogonal hexes. And then you can use that in an unstructured block to rapidly generate your volume topology, or volume cells, I should say. And if all else fails, you can always revert to triangles in very difficult regions. So with that, I thank you for your attention, and thank you for watching the video today. I encourage you to check out our other Let's Talk Meshing events, our webinars and videos that we've put together, the aneurysm and volute in particular we talked about a little bit more today. Also, I encourage you to visit our GitHub repository to look at the scripts we have available and start using those to enhance your workflow. And then if you have any questions, feel free to contact us at letstalk@pointwise.com, or you can send us a tweet with hashtag letstalkmeshing. We're also going to be monitoring the YouTube comments for questions and all that. So I look forward to your questions and appreciate your time. Thank you very much.